Clay-based tools for modern pollution exposure control. Kaylee Harrison. Engineered clay is revolutionizing environmental risk mitigation, thanks to decades of research led by Dr. Timothy Phillips at Texas A&M University. Originally studied for its effectiveness in binding aflatoxins in contaminated food supplies, refined clays are now part of a comprehensive strategy to reduce human and animal exposure to a broad class of chemical contaminants. These layered mineral sorbents are chemically structured to trap pollutants through surface adsorption. Once ingested or applied topically, they limit the absorption of toxins such as aflatoxins, pesticides, and heavy metals. Products based on this research are already used in livestock feed and human dietary supplements and have been trialed in regions where aflatoxin exposure is chronic. What sets this approach apart is its adaptability. Studies showed that clay-based binders remain stable under cooking conditions, allowing them to be integrated into traditional food practices without losing efficacy, a factor that makes them viable in lower resource settings and humanitarian contexts. Targeting PFAS and VOCs through multi-pathway solutions. Building on early food safety applications, the Texas A&M team expanded its scope to address PFAS, forever chemicals, volatile organic compounds, VOCs, and other persistent industrial pollutants. Through the university's Superfund Research Center, Phillips leads the development of oral sorbents and topical formulations for high-risk scenarios, such as flood zones and fire-damaged industrial areas, where exposure risk rises sharply. The ingestible formulations are nutrient-enriched and designed to bind pollutants in the gastrointestinal tract before they cross into the bloodstream. Meanwhile, a topical barrier cream, intended for first responders and community use during disasters, offers dermal protection by forming a temporary shield against contaminants in floodwater or ash. These interventions are practical, portable, and relatively low cost. They don't rely on extreme decontamination methods like thermal destruction, which are technically difficult and often financially out of reach. Instead, they focus on exposure prevention, helping people manage risk while long-term remediation efforts continue. Another research track explores the use of plants and chlorophyll as natural filters. By studying pollutant accumulation on leaf surfaces and within plant tissues, the team is identifying vegetation that could play a role in ambient air purification or soil stabilization. Early data also shows promise for chlorophyll-based compounds in filtering indoor VOCs, including benzene. Collaborations with experts in urban planning and green architecture are underway to translate this data into tangible strategies, particularly for integrating sorbent-capable plantings with clay-enhanced soils in residential and industrial developments. As the industry grapples with long-lived contaminants like PFAS and VOCs, clay-based and biologically derived sorbents offer an interim solution, scalable tools that reduce exposure without the infrastructure demands of full-scale removal. This research supports a shift toward integrated mitigation, where materials science, toxicology, and environmental planning intersect to reduce liability and safeguard health in contaminated or high-risk environments.